I'm Connor Doherty of the U.S. Bureau of Labor Statistics. The presentation is accounting for sampling errors in seasonal adjustment. Okay, Connor, are you here?
Yeah, I'm here.
Okay. Proceed.
Okay. Go ahead and screen share. All
right, looks good.
right, thank you. Okay, hello everyone. I'm Connor Doherty. I'm going to be presenting some findings on accounting for sampling error in the seasonal adjustment of National Labor Force Series. This was research done by 4 of us at the Bureau of Labor Statistics, Tom Evans, Mikhail Sverchkov, Reed Rotak, and myself. So I'm going to start off with just some introductory information and some information about the current population survey. And then we'll move into our model and estimation method, and then we'll look at our results. So starting off with that introduction, government stat agencies always strive to produce reliable labor force statistics, even with constrained budgets. And this is even more important nowadays with the rising non-response rates that a lot of us are seeing. And one way we can try and help with these issues is by accounting for sampling error inside of our models. And this sampling error component can be removed from our seasonally adjusted series to improve reliability, and it can also be removed from the unadjusted data. Now, a little bit of information about the current population survey, which is where the series that we're looking at today come from. So the current population survey, or CPS, is a national monthly household labor force survey. After non-response, we've got about 42,000 households, and that turns out to be about 80 to 82,000 individuals. Like I said, we had a lot of series from this, many labor force estimates, including the monthly unemployment rate. And the real important thing here that will come up is the 484 rotation pattern that CPS uses. And what this means is when a household enters the survey, it'll be surveyed for 4 months, and then it leaves the survey for 8 months, and then it returns to the survey for another 4 months. So we get 8 months of data from a household. It's just spread out over those 16 months in 4-month blocks. Currently, we directly seasonally adjust 163 monthly and quarterly national series from CPS, and this is using seats, which ignores sampling error. So now let's talk a little bit about our model and the information that comes with that. So with the CPS sampling error, there are 2 things that we're going to need to account for. The first is variability due to small samples, and the other is the overlapping sample design. That was the 484 design, and this causes strong autocorrelations in the sampling error. The way we account for these is with a signal plus noise model, where the monthly estimates are treated as a stochastic time series obscured by survey error. And this is this is similar to what's currently being used by Dick Tiller for state employment and unemployment estimates. So for our very large, highly aggregated series like total employment, we get very reliable estimates, but the same can't be said for many of our demographic series. Our sample is just spread too thin for those for acceptable reliability, and that's something that the sampling error model is going to help with. There's many papers, many examples on how to account for sampling error in your time series model, and some of those are listed here at the bottom if you're interested in this topic more. So now we get to our model. This is what it looks like in additive form. We've got, just going from left to right here, small y is our direct survey estimates, capital Y is our true population values, and E are the survey errors. And the survey errors and population values are independent of each other. Let's look a little closer at those survey errors. That's what we're interested in today. So the complex design of the CPS induces heteroscedasticity and autocorrelations in the sampling error, which gives us these two properties. So the sampling error is normally distributed with mean zero, variance sigma squared, and note that the variance here is time dependent. And then we also have that the covariance between the survey error at two different time points is rho times the standard deviation at those 2 points. And this rho is the sampling error autocorrelations, which are fixed for a given lag length. You can see that with the absolute value of the time difference here. So those are two properties of the sampling error. And this is how we end up modeling the sampling error. So we model it as a stochastic process in state space form. And we have two components here. We have gamma t and E star t. So gamma t is a scale factor, which accounts for the changing CPS variance. And then E star t is an AR15 process, which models the autocorrelated sampling error. You'll note right after this AR15 here, we have this AT. That AT is an uncorrelated independent disturbance term with zero mean and fixed variance. But the reason we use this AR15 process is because it captures the most important correlations induced by the sample overlap. And remember that sample overlap is from the 484 rotation pattern that we use in CPS. So that's why we use this AR15 model. So this is what our model ends up looking like. We break it down into these components, and this is in the form of a structural time series model. So going from left to right through all these terms, we've got T is the trend cycle component, S is the seasonal component, I is irregular, SE is sampling error, O is outlier, and H is the holiday component. These last two are included as needed, depending on the series and the time. And then these first three, T, S, and I, make up the signal. So this is the signal plus noise model. So let's look a little more at each one of these terms, just real quickly. So T, the trend cycle component, consists of a local linear trend with a level and slope to form an integrated random walk. The monthly seasonal component, S, is specified with 11 trigonometric terms corresponding to the 12-month frequency and its 5 harmonics. And then our outlier component, O, consists of our 3 outlier types, which would be additive outliers, temporary changes, and level shifts. The irregular component, I, is a residual, and it's not explained by any of our other components, and it has a single white noise disturbance. And then the sampling error is another unobserved component, but we do know its variances and covariances. If you choose to leave sampling error out of your model, so if you ignore it, that will affect your other components. So our signal terms, trend, seasonal, and irregular, all have disturbance terms. The variances for these are known as hyperparameters, and those determine the properties of the components. So that was our model. Now we're going to talk about our estimation method. So we make a forwards and a backwards pass through our data using the Kalman filter and a backwards smoother. Specifically, the forward pass is done using the forward filter, and that's applied throughout the current year. And then at the end of the year, we do our backwards pass, which is done with a smoother, and that's applied to the historical data. What this does is every time we're adding new observations, we update our entire knowledge of the system. So the Kalman filter is just a natural way to forecast seasonal components, to get projected factors, or to make concurrently seasonally adjusted estimates, and that's because it was designed to do that. It was designed to produce current period estimates. What it was not designed for is to revise any prior estimates. So the Kalman filter isn't great at producing historical estimates for your data, and that's why we end up using the smoother. So the smoother goes backwards from time n through time 1 and revises our Kalman filter estimates to account for all the information that we have in our series. Now, just a little bit of information before we get to the results. So for our diagnostics, we looked at plots of the spectrum, components, and prediction errors to examine the quality of our adjustments. And then we also applied Box-Young heteroscedasticity and normality tests to the standardized prediction errors. So now onto our results. We looked at 28 directly adjusted series. These are from 2003 to 2023. And then we also looked at the national unemployment rate, which is an indirectly adjusted series. I do want to note that 9 of the series that we looked at are not currently being adjusted because they didn't meet our standards for adjustment. And one other thing is that if we look at revisions, those can be a little larger when accounting for sampling error, when comparing it to seats, which is what we're currently using. And this is because of the smoothing that we do. But we believe that the gains that we get from using the sampling error model far outweighs the slightly larger revisions that we'll see. Now let's look at those results. This is a table of our absolute month-to-month changes. We've got 9 just randomly selected series that we looked at. And here we've got the month-to-month changes for seats and the month-to-month changes for our sampling error model. And you'll see across the board, the sampling error model has smaller absolute month-to-month changes. So our series are less noisy, and we'll see a little bit later on the plots, it's easier to interpret and see the trends, see what's happening. Some of these series, though, have huge improvements from one model to the next. Specifically, these first 2, discouraged workers and unemployed Hispanic male teenagers, we see a huge gain in our month-to-month changes here. And then the same thing down here with employed agricultural unpaid family workers and unemployed Asian teens. Those 2 also saw a huge decrease in those month-to-month changes. So now let's look at some plots. So this is a plot of our estimates for unemployed Black female teenagers. This is a pretty noisy series generally, so this is a good one to look at to see the difference between seats and the sampling error model. So in blue, we've got the seats model, and we can see it's pretty noisy the whole time. If we compare that to green and red, green is the smooth sampling error model, and then red is the forward filter sampling error model. So that's like the final step and partway through the process. And we can see if we follow those 2, they're quite a bit smoother than the seats model. Generally, it's easier to see the trend, it's easier to interpret, and we'll see that throughout the rest of these plots. So this is unemployed Hispanic male teenagers. We see a similar thing. Seats in blue is pretty noisy, and then sampling error, the sampling error model cuts right through it, smoother. Here to see what's going on. And specifically, the seats model is the final seats model, and the sampling error model is the smooth, so the final step of that. Here we've got our the national seasonally adjusted unemployment rate, again comparing seats in blue to sampling error in green. Here seats is the concurrent seats, so not the final estimates, and this is the forward filter sampling error. So again, not the final estimates yet. And we can see again, seats is it's a little, or sorry, the sampling error is a little smoother here. Seats is a little more noisy. And if we look at the final estimates for unemployment rate, we see the same thing we saw before. See, the sampling error model is cutting right through the seats plot. You see that trend from the sampling error model, and seats is a little noisier. Now this is our unemployment rate. So this is a very highly aggregated series, very large series. So we're even seeing a gain with the model change here. And when we publish the unemployment rate, it is very heavily rounded. It's rounded to the nearest 10th. And that's what this lists. So again, we've got seats in blue, sampling error in green, but now it's just rounded. And even after this heavy rounding, the sampling error model still looks a little smoother. It's especially noticeable here in this run from September 2022 to April 2023. Seats is bouncing between 3.4 and 3.6, whereas sampling error model is consistently 3.5. So even with a large, highly aggregated and rounded series like our national unemployment rate, we're still seeing improvements in smoothness for the sampling error model. So that's the last plot we've got. Now just some closing words. We hope our work shows the importance of accounting for sampling error when seasonally adjusting CPS national series. We saw gains in accounting for sampling error in all of the series that we've modeled so far. And many of the series that are not currently being seasonally adjusted, we can now consider for adjustment using the sampling error model. Even we saw gains with larger series like the national unemployment rate. So it's not just these small demographic series that we saw improvements with. And one important thing is that the gains we see from this model are obtained using only the information we have in the CPS. We don't need any external data. And the runtime is comparable to what's currently being used. So this wouldn't end up slowing down production for our press releases. And just one last note, once you do have the sampling error correlations, implementing the rest of this process isn't too difficult to do. So yeah, that's all we've got. If you have any questions, feel free to email myself or Tom Evans, and thank you for listening.
All right, great, thanks. Great talk. So we have time for a few questions before our break. I'll make a comment. I think you want to look at not just smoothness and month-to-month changes, but maybe some other criteria as well, like looking at in frequency domain, because you could, if your criteria is just smoothness, you can use different kinds of filters that would get a smoother and smoother output. And so I don't know that I even care about smoothness of month-to-month changes for quality seasonal adjustment. Ultimately, I want to make sure that there's no seasonality left. So that may be something you want to think about or add. That's just a comment. And then I had a question. All the series you're looking at in CPS, are they monthly and quarterly?
Yes, monthly and quarterly.
Okay. But you guys do have weekly series at BLS, but they're not in the CPS. It's something different, I guess.
Yeah, they are different. I don't believe there are any weekly ones in CPS, okay. So those are separate. Yeah.
Yeah. Okay. Yeah, because I was wondering whether your methods would be able, whether you could carry over that methodology to handle weekly series with sampling error.
Tucker, this is Tom Evans.
Seems like
the answer is yes to that.
Yeah, hey Tom.
Oh, the answer is yes to that, and we do use the structural models for the national UI weekly estimates, seasonally adjusted estimates, but it's an administrative series and they don't have any sampling error. But if it did, you could apply it in a similar manner.
Okay, nice. Thank you. Let's see. Anybody else have questions? If you do, you can just take off your mic and ask. Now, Bill has his hand up, so let's go to Bill. Bill. Yeah, Bill, do you have a question? You have your hand up. Can't hear you, though. Okay, anybody else? I'm looking at the chat here.
Oh, hello.
Yeah, go ahead.
I have a quick question about what tools do you apply the sampling error adjusting models?
You mean like what?
I mean,
programming
for
language?
the estimation, I understood your modeling, and then in terms of how do you get, or in other words, how do you get those different curves?
Maybe it's a question about the software.
Oh, right. Yeah. So, or any packages.
Yeah. Okay, we're doing this in SAS.
Oh,
That's
got
just
you.
what we're familiar with. I'm sure you would be able to do this in like R, for example. I'm not sure what packages you would need to use for that, though.
So this is already built in SAS then?
Yes.
Okay.
Yes.
Thank you.
Yeah, there are packages for doing structural time series and state space types of things. I can't remember offhand, but I have used them in the past. Okay, any other questions? Still have a couple minutes in the session.
Bill has his hand up.
Yeah, he's had his hand up for a long time, but I don't hear anything from him. Sometimes people put the hand up and then forget it's there.
Oh, then I do have another question. So, would you consider doing confidence bands for your curves?
Yeah, I'll answer that one. This is Tom Evans again. Yeah, we can do that. There's some different ways to do it. One of the ways we've looked at in the past is using the observation weights, like that we could use for any kind of model like seats and so forth. I'm not exactly sure how we're going to end up doing it because Dick Tiller has some other ideas about how to do it. And so, but yeah, that would be coming. We can do that, of course.
Oh, I asked this because sometimes I feel if you introduce sampling errors in the models, it can introduce more variation in your confidence band. So you might end up having wider confidence bands than without the sampling error term in there. So I'm just curious, how would that affect your confidence band for this case?
We haven't actually done it for the sample and error models yet. Dick Tiller's been doing this for many years for the WOWS program over at BLS. And I'm not exactly sure about the results that they get compared to, say, using seeds.
Okay, so Bill actually put his question in the chat, so I'll read this out. What are your standards for publication? Are they variances of the estimates or smoothness of the seasonally adjusted series?
I'll try to answer that again. That's a good question from Bill. And I don't know if we don't really have any explicit standards for this kind of thing. In the past, we've always just either used X11 or seats. In fact, we're using seats for all these models now. And we just, I mean, so there hasn't, this is the first time there's been a, kind of a big challenger to something from X13. And so, it's nice if they're smoother because it can make it a lot easier to evaluate the series. And, but yeah, that's a really good question. I don't have an exact answer for that.
Okay, maybe
I'm
something
sorry
to
that Bill's
cogitate upon.
mic is off because I'd like to hear him say more about that.
Yeah, maybe offline. I think we have to close out the session. So thanks to both Guy and Connor for great talks, very stimulating. Thanks everybody for attending. And now we're gonna take a 10-minute break. So see y'all later.